I am Professor Vijay Chalavendra from Department of Mechanical Engineering, University of Massachusetts, Dartmouth. This is regarding multifunctional natural fiber composites. These are series of presentations I will be posting on this topic, and this is the first one as a part of this series. And this project is sponsored by National Science Foundation of United States of America. Natural fiber composites has become very popular these days, and they found many applications. One of the applications is shown here on this slide, where they used as many interior parts such as doors and other parts as you see in this picture. In addition to that, if we want to use them for load-bearing applications, there are some applications in the world where a footbridge has been made purely using natural fiber composites, having the flax fiber, which is a natural fiber, reinforced polymer composite. In this study, we wanted to make it multifunctional. To make it multifunctional, we add carbon nanotubes and carbon fibers in the composite. As you see in this picture, carbon nanotubes are infused in the epoxy matrix, where the epoxy matrix has been used in the vacuum infusion process, and carbon fibers are reinforced in between the laminates using a electroflocking technique. This combination of carbon fibers and carbon nanotubes will generate a conductive network which is three-dimensional in nature, which is going to give us very sensitive network under mechanical loads to monitor the damage in these systems. The first thing is composites fabrication. In this study, we use jute fabric as the reinforcement and the epoxy as the matrix. Jute, as you know, is a hydrophilic in nature. It absorbs a lot of moisture. We do not want to have jute fiber absorbing moisture under real-life applications when this composite is used. Hence, we wanted to make it hydrophobic. To make it hydrophobic, we treat these jute fibers in two steps. One is alkali treatment using the NaOH solution and saline treatment. These two will eventually make this jute fiber hydrophobic. We will be showing you the results in the next coming slides. In addition to that, we need to do a good dispersion of carbon nanotubes in the epoxy matrix. Otherwise, we cannot generate a good conductive network in the system. We also wanted to see the effect of having a jute fiber orientation, such as having a unidirectional composite as well as a cross-ply composite, which is 090 composite. And in this part of the study, we wanted to investigate the effect of jute fiber orientation on the conductive network. As I mentioned, we employed a wet flocking technique to reinforce short carbon fibers between the jute laminates. And then we employed the standard vacuum infusion process along with the compression molding to fabricate these composites. The reason why we employed both techniques is to generate at least 60% volume fraction of the jute fabric in the composite. As you see in this picture, we have a dispersion of carbon nanotubes in the epoxy matrix. This is accomplished by employing a combination of shear mixing and ultrasonication. First, we mix required amount of carbon nanotubes in the part A, which is the resin part of the epoxy, and then we use a combination of shear mixing and ultrasonication to disperse these carbon nanotubes both microscopically as well as macroscopically. Ultrasonication process will disperse the carbon nanotubes at nanoscale, and shear mixing disperse the carbon nanotubes macroscopically, which is very important for us to avoid segregation of these, clustering of these carbon nanotubes. Once that is done, it was put in the vacuum chamber to remove any air bubbles induced during this process of mixing. Later, the part B of the epoxy, which is the hardener, is mixed in this as a part of the next step. Then again, one more time, it was combination of shear mixing and sonication was performed for a few minutes before it was again used in the vacuum chamber to remove any extra air bubbles induced in the process of mixing. Now this mix is ready to use to make the composite. The important process we employed to reinforce carbon fibers, short carbon fibers. In this study, we use two different kinds of carbon fibers. One is 150 microns, other one is 350 microns long carbon fibers. They are of around 7 microns in diameter. They were reinforced normal to the jute fabric using a wet flocking technique, where you have two conductive plates. These two plates are separated at a far distance, and at the bottom plate we spread carbon fibers evenly, and then we apply a high voltage of 60 to 100 kilovolts between these two plates. When it is applied, all these carbon fibers will go and attach to the jute fabric, where you have a tiny layer of epoxy which was previously made with CNTs, so that these carbon fibers will get stuck there and not fall down. So this way we reinforce short carbon fibers, and once we make these short carbon fibers reinforced fabrics, we stack them up, and then we apply a vacuum infusion process to make the composite in addition to compression molding. Once the composite sheets are available to us, we cut them into rectangular strips, where we use a 4.4 circumferential probe measurement technique to measure the resistance of the composite. In this presentation, we wanted to understand how various parameters we control in the flocking process, how it's going to affect the electrical resistivity of the composite. Hence, we employed Keithley instrumentation system, which is high resolution, highly accurate measurement system, where we supply a constant current through the outer probes, which are separated by 1 inch, and then we measure the voltage between inner probes using a set of electrometers. These electrometers have high impedance, which will prevent any current leakage. At the same time, they will provide accurate voltage measurements when we are testing high resistance material like this. And these two electrometers will provide differential voltage to the digital multimeter, which is model 2000 of Keithley instrumentation. Later, we captured the voltage measurements in the LabVIEW for the data acquisition. The details of the measurement, the details of this instrumentation can be found in the below reference of our paper published in Polymer Composites. Getting into the results, I wanted to present here the effect of alkali treatment and the saline treatment, which is APTMS treated saline, on the hydrophobic nature of the jute fabric. Now, as you can see, the raw jute can absorb water in the water wicking experiment, where it can absorb up to 80 millimeters of long absorption. However, when you do alkali treatment, we remove lignin and hemicellulose from the jute fiber, which will actually open up the jute fiber. That will allow to absorb more water compared to raw jute. However, when you do APTMS saline treatment, all the jute ions in the jute fiber would actually become hydrophobic. As you can see, the green dots, which are on the x-axis, where they have zero water absorption. Hence, we want to confirm that it's very important to prepare the jute fabric hydrophobic before we use them in the composite fabrication. This slide is very crowdy, but this slide gives us the entire picture of theoretical measurements what we captured in this experimental study. We have, in the horizontal axis, we have different fiber densities of carbon fibers, and we have different fiber lengths. As I mentioned to you, we employed two different fiber lengths, 150 and 350, and we have two different laminate orientations, which is unidirectional, which is 000, and cross ply, which is 090, 090. And then we also tried two different amounts of carbon nanotubes and see the influence of weight percent of carbon nanotubes on the results, which is 0.1% and 0.025%. These are very, very small quantities of carbon nanotubes. We deliberately put these small amounts because carbon nanotubes are very expensive and we do not want to put too many, and we want to achieve the required electrical resistivity with a smaller amount of carbon nanotubes. As you can see in this picture, amount of carbon nanotubes did not play a significant role. You see a similar trend for 0.1% and 0.25%. Very marginal difference you can see between that. However, if we see the laminate orientation, there is some decrease in 090 orientation compared to 000 orientation for both carbon fiber lengths. However, if you have a carbon fiber length of 150, they have very high resistance because 150 carbon fibers cannot penetrate through the laminates to generate a good network. However, if you use 350 carbon fiber length, you can see very small resistance values. That is possible because 350 carbon fibers are able to penetrate through the laminates, which will generate very good conductive network. As you can see, the flock density of carbon fibers, in case of 150 microns carbon fibers, you see an exponential decrease of resistivity as you increase the flock density of carbon fibers from 500 to 2000. However, you do not see such a decrease in case of 350 carbon fibers because 350 long carbon fibers generates a decent network even if you use 500 flock density. However, for the same flock density or 150 microns carbon fibers, the resistance is very, very high. As you see there, it was around 10 power 9 ohms per ohms meter. I would like to show you here the resistivity values with and without carbon nanotubes. We wanted to achieve resistivity values, decent resistivity values, not putting any carbon nanotubes. As you can see here, if you do not put any carbon nanotubes in the system for 150 carbon fiber length composites, you cannot pass current through the system for the flock density up to 1500 fibers per millimeter square. However, you can only send the current if it is 2000 fibers per millimeter square flock density in case of 150 microns carbon length composites. If we take into account of 350 carbon fiber length microns carbon fiber composites, we can send the current even with 500 fibers per millimeter square carbon fibers. So 350 microns carbon fibers penetrates through the laminates, which will give us good network even without any carbon nanotubes for both systems of 000 and 090. So this is a good observation that without carbon nanotubes, you should be able to generate a conductive network within the composite of carbon fibers of length 350 microns, even with a flock density of 500 fibers per millimeter square, which is really exceptional. Hence, I would like to conclude this presentation with a few conclusions here. So water Viking tests really demonstrated that surface treatment was very successful. We were able to make it hydrophobic, and the jute fiber volume fraction we achieved as much as 60% in these composites, which is not common in the previous studies. And variation of CNT amount of 0.1% and 0.025% has no significant effect on the electrical resistivity of the composites. And the effect of flock density is more significant for shorter carbon fiber length of 150 microns. And 350 microns carbon fibers composites generated better conductive network with the neighboring fibers as well as with the CNTs, both between the laminates as well as within the laminates. And resistivity marginally lowered for 090 orientation compared to 000 orientation. In case of no CNT situation where current could not pass through composites of carbon fibers of 150 micron long, however, the current is able to pass through even for a small flock density of 500 for the composites of 350 microns long carbon fiber composites. Thank you very much.